Hi guys, Utkarsh here. So actually have a very mind-blowing, very interesting solution to this problem E from yesterday's contest. So this is the problem E, unordered swaps. And like I'm not sure if the editorial is out yet, but at the time I'm recording this video, I think there's no tutorial for problem E. And this contest is basically made by my college juniors. So I asked them what their solution was, and like it's different from my own solution. So that's why I'm making this video. And yeah, so in this problem, it's like you are given a permutation and there's some person Alice. So she chooses a way to sort this permutation using the minimum number of swaps. And then this list of list of swaps is shuffled and given to you. So you have to recover one of the correct orders in which if these swaps are performed, then the permutation would be sorted. So it's kind of like, okay. Yeah, so it's kind of like, let's say we have some permutation like 2, 3, 4, 1, and then the minimum number of swaps that are required to sort this permutation, they are given to you. So the swaps are like 1, 4, 2, 1, and 1, 3. So this solution means that if we perform them in the order 2, 3, 1, that means first we do this, then we do this, and then we do this. So then this permutation would be sorted. So let's try it out. So if we do 2, 1 first, then it would be 3, 2 because we swap these two. And then if we do 1, 3, then here we will have a 4 and here we will have the 3. Okay. And then at the last we have to do 1, 4. So then this would be 1 and this would be 4. So finally we got 1, 2, 3, 4. So yes, basically that's what we have to do. Now, because I want to get into my solution, I will basically fast forward the initial part a little bit. So kind of what's happening is that in a permutation, like in a permutation, there are cycles basically. So if we have something like 2, 3, 4, 1, so it's like in the position of 1, there's 2, and then in the position of 2, there's 3, and in the position of 3, there's 4, and in the position of 4, there's 1. So basically, something like a cycle is there, and there can be multiple cycles in a permutation. Let's say if we had 6, 5, so then the next cycle would be 5, 6, and 6, 5. So there are these kinds of cycles in the permutation. And what happens is that if you have like n cycles in a, like, I mean, if there are n total numbers and there are 2 cycles, so then the number of swaps that are required, the minimum number of swaps are always n minus the number of cycles. Okay, so like in this case, it can be done using 6 minus 2, that is 4 swaps, and then in the input there was only 1 cycle and there were 4 elements, so it could have been done in 3 swaps. So yeah, and this is because it's kind of obvious that if we have like multiple cycles, we can just solve each of them separately. And what we can do is, in one move, it is always possible to put one element in its correct position. So that will reduce the number of elements in that cycle by 1. And ultimately, only one element would be remaining and that would be in the correct place. So that's why for each cycle, it's the number of elements in that cycle minus 1. So in total, it's the number of total elements minus the number of cycles. So if we can solve one cycle separately, then we can solve the entire thing, because we just have to solve all of the cycles. So one thing is quite obvious, is that if we have like multiple cycles, so if we have multiple cycles, so what will happen is that there will be no swap between elements from this cycle and this cycle, because that would kind of connect these cycles. But to have the minimum number of moves, because it is given in the problem that the permutation is sorted in the minimum number of swaps. So to have the minimum number of moves, we will never merge 2 cycles. We will always either divide 2 cycles, divide a cycle into 2 different cycles, or we will take one element out. So that's also kind of like dividing that cycle into 2 different cycles. So yeah, we will never like these 2 different cycles, they will never interact with each other. So that will be definitely there. Now next thing what we can notice is that whatever these swaps are given, if we make a tree using these swaps. So we can kind of like make a tree using these swaps, an ordered tree. Just put the edges, like there's an edge between 1 to 4, there's an edge between 2 to 1, there's an edge between 1 to 3, and so on. So this kind of tree we will get even in the next problem, even in the next test case. If we make, we will actually get a forest in this case, but yeah, 1 3 2 5 and then 3 6 and 6 4. So yeah, in this case we are getting a forest, and in some cases we might get a tree. So each tree in that forest is representing a single cycle. So that's what's happening here. But what we want to do is, like we can assume that basically if there's a tree here, so no matter what the values are, we can rearrange them in any order using n-1 moves, and whatever swaps are given, these are the edges. So this is already connected. So basically we can rearrange anything from anywhere within a tree. So what would be the correct way to do it? So that is something like, when we do these swaps, like let's say if we have two nodes and there's an edge between them, and then there are more nodes here, and then there are more nodes here, and so on. So when will we do this swap? We will do this swap, and one thing should be clear, that once we do this swap, we won't do it again. So this edge would be disconnected, these values would be changed, and then we will get two separate trees. So because we will get two separate trees, what we want to do is, we want to make sure that all the values that should be in this tree should be in this tree after this swap, and all the values that should be in this tree should be in this tree after this swap. So basically what will happen is, let's say here we have like I'm marking this as blue and I'm marking this part as green. So what will happen is, we will make this swap when this particular node would be green and this particular node would be blue. And by blue and green, I mean, like, you know, I'm partitioning it into two parts. So at this stage, what I will do is, I will put this green vertex here, and I will put this green value here, I will put this blue value here, and then I will have an entire blue tree here, and I will have like a green tree here. So by blue and green, basically what's happening is that like all the green values should be on this part of the tree, and all the blue values should be on this part of the tree. So basically this is something that we're doing, and I will give you a small example as well. So let's say the tree was like 5 4 3 2 1 6, something like this. Okay, so this was the tree, and these are the this is the tree that we have formed using the indices. Okay, now again the permutation will put some values at each vertex. Like let's say at the first position, currently we have the value, let's say we have a 5 here, and then we have wait a second, so let's say we have a 6 here, we have a 2 here, and then we have a 5 here, and then we have a 1 3 and 4 here. Okay, so now look at this edge. If we perform so if we perform this swap, if we remove this edge and if we perform this swap, what will happen is, here we will have the value 5. Let me take another color. Yeah, so here we will have the value 5, and here we will have the value 1. Okay, so now look at this part. Here the indices are also 1 to 6, and the values are also 1 2 and 6. And here also, if we look at this part, the values are the values are 4 3 and 5. Yeah, if we look at this circled part, the values are also 3 5 and 4, and the indices are also 3 5 and 4. So obviously this part is also solvable, this part is also solvable. But if we, you know, if we pick some other edge first, then what will happen is, so if we pick some other edge first, let's say if we pick this edge first, yeah, so if you pick this edge first, what will happen is, here we will have a 1, and then this edge would be lost, and here we will have a 4. So the problem here is that we put the we put 1 on index 3, and then there are no swaps that can connect it to the actual one where it needs to go. So that's why we will always connect an edge. We will always basically disconnect an edge and perform the swap in such a place such that after doing this, the two trees that we get they should have the values which are same as the indices that are present in that tree. So that's the basic idea of the solution. So that's what I want to do. But it turns out it's quite difficult to do this. And here's why my solution is interesting, because it involves multi-set hashing. And basically, multi-set hashing, in simple words, is a way to compare two multisets in just a single operation. So in O1, it can check if two multisets are the same or not. So what I'm going to do here is I'm going to show how multiset hashing works. So let's say if I have a lot of elements and let's say I have a multiset 2, 5, 4, 3, 5, 7, something like this. And then I have another multiset. It can also be like 2, 4, 5, 3, 7, 5, something. Okay. So obviously these two multisets are same. You can see these multisets are same. But how will you check if these multisets are same? It's a difficult process. We have to check the elements one by one. So for this, what we can do is we can use a technique that's called multiset hashing. So in multiset hashing, what we do is we hash this entire multiset and then we get a single value. And then we hash this multiset as well and we get another value. Now, if both of these values are equal, that means there's a high probability that these multisets are also equal. Although it is not deterministic, I mean, there's always some room for, some random error. That means, but we want the probability of that error to be very low. And I'll explain how that works. But yeah, so basically what we do in multiset hashing is that each element of the multiset, like each element in general, is given a random value. So we have like a random of, we have an array of random. So random x equals a random value. But it's fixed for every element. So basically, if we have this 2, so it will have some random value like let's say 2, 3, 5. Like it can have a very long random value between 1 and infinity. Okay, so it has a very big random value, and then this element also has a random value. This element also has a random value, but two equal elements will always have the same random value. So rand 5 is like always equal to rand 5. And then what we will do is we will just add all of these. So to hash this multiset, the answer will be just rand 2 plus rand 5 plus rand 4 plus rand 3 plus rand 5 plus rand 7. So we will have the sum of all elements. So sum of rand of all elements. So like sigma rand x. Okay. So we can have the sum of all these elements. And now it's simple to see that we can easily insert or delete any element. So to insert any element, just add the random value of that element. And if we have to delete an element, we can just subtract that random value. So since all of these values are random, then the sum of this will also be random. So, and these values are like quite large, so such that the sum would probably overflow, and it would be the sum mod something like whatever the sum is, it would be mod 2 to power 64. And 2 to power 64 because like when you add with overflow, it rolls around. I mean, pretty sure you're familiar with that. So yeah. So this value, since it is random, it would be any random number between 0 to 2 to the power 64 minus 1. Okay, so this would be any random value between this. So what is like, if the two multisets are same, then this hash would be same for two multisets. That's obvious. But what if these are not same? Then what's the probability that these random hashes can be same? So it's just the probability of two random numbers to be equal, and that is 1 upon the total possible values. So this will be 1 upon 2 to the power 64. So this is a very low value. It's around 10 to the power minus 18, I guess. 10 to the power 18, 10 to the power minus 18 is a very low probability of failure, and we can work with this. So that's why we won't get the wrong answer verdict, because the probability of our solution failing is very low, because each comparison has only 10 to the power minus 18 probability of failing. And even if we have like 10 to the power 7 comparisons or something, then also the probability will be very much lower than 1. So we can be assured that this type of multiset hashing will work. So what will we do with this multiset hashing? So what I will do is I will make the tree. Okay. And now basically I want the hash of this element, like for this element. Like let's say if, I mean, this is a big tree, okay? And I want to check whether I can swap this edge or not. Okay, and let's say I have made the tree in such a way that this is like this is the parent of this vertex. Okay, I have rooted the tree somewhere. Okay, so now let's see if we can cut this edge or not. So we will cut this edge when, let's say, all of these vertices would be red and this would be red. So we will put this red vertex here, and then whatever we have here, we will put them above, and then we will cut this edge. So that's why I want to make sure that like all of these are red. So let's say I have the indices. So indices can be 1, 2, 3, 4, 5, 6, 7, 8, or whatever. Like it can be in any order, in fact. But yeah, so I will just change the order a little bit. Okay, so like this can be in, just to explain that this can be in any order. Okay, so yeah, yeah, whatever. So now on this vertex, I will store the hash of the multiset hash of all these indices. So this will be like sum of hash of indices. So like this hash of 8, hash of 3, hash of 4, hash of 5, and so on. Okay, so I have the sum of hash of all of these indices, but I will also subtract the hash of all the values that are present in this tree. Like here, like let's say on this 3 we have the value 9, and on this like these are just the array indices, right? So we will have some values, right? So we will have p3 here, and p3 is, let's say, 9 here, and then 8, and then here it could be like 4, 5, 1, whatever. Okay, so like we can have different values here. So we will add the hash of all the indices, and then we will subtract the hash of sum of values. Okay, so we will add the hash of indices, and we will subtract the sum of values, and then we will also like we will exclude the vertex. So like on this 8, even if we have like 7, even if we have like 5 or 6, we won't include this in this part, right? So we're not including this because this wouldn't be in the subtree after the swap. So basically whatever this value is, we don't care because it will go out of this, right? In fact, what we do care about is this value, like whatever we have here. Let's say if we have a 10 here, so we care about this value instead of this value, because after the swap happens, this will come down and this will go away. So after this swap happens and we have the 10 here, so we will cut this edge only in the case that all the indices that are present here should be equal to all the values that are present here. So basically this entire thing plus this thing should be 0. I mean, this thing minus this thing should be 0, because we have subtracted all the values except this, and if we subtract this as well, then it would be the same as all the indices that are there. And since all of the indices and the sum we already have, so this thing should be 0, right? So again, what I'm saying is basically take the sum of the hashes of all the orange things, and then take the sum of the hashes of all the blue things except this one, but include this as well. So then that should be 0. And in that case, we will perform this swap. So that's the basic idea. And how did I implement this? Because even this is hard to figure out, like where do we have this kind of 0? Like where will we find these zeros? So to do this, what I did was, like, I have a tree. Okay, so let's say this is a vertex, and then like this is a vertex, this is the parent, and this is like the grandparent. Okay, But anyway, so what will happen is I will, let's say if I check this vertex, okay, so I'm checking this vertex. So what will I do? I want, it can have a multiple children, right? It can have multiple children. So what I want to do is I want to see whatever value I have here, whatever value I have here, I want to find this value somewhere in these children, because these are storing the sum of the indices minus the sum of values except this vertex. So if it is correct, then it would be equal to this exact value, because then this value would go inside that and it would make it 0. So I will try to find this value in all of these children. So basically I can keep a set of all the values that I am getting here in the parent node, and then I can check if this value is equal to any of these using a set operation in just login time. And if I do get that, then I will make that swap. Let's say if here that hash is equal to the value, so I will just cut this edge, I will make the swap, and I will go on. So what happens now? So once I do this swap, so basically once I do this swap, so once I swap these two, what will happen is that the value here will be changed, value changed. Okay, here the value is changed, and the hash that we have stored is also changed. Okay, and here nothing is changed, but the hash of the child has changed, and since it is storing a set of all the hashes of the children, so that's why this will also get changed. So like this is also affected. Basically what I'm saying is that this edge is now affected. Like earlier this edge could have been wrong, but now it could be correct, right? And then all of these edges are definitely, like all of the red edges are affected. Like they might be the next edge that can be taken after we perform this swap. So after this swap has been done, all of the red edges might become relevant. So that's why what I will do is, and only these edges will be relevant. All of the other edges won't be relevant. Like if they were relevant earlier, they will still be relevant. If they were not relevant, they won't be relevant now as well. So yeah, so what I will do is I will, and I can say that all of these edges are connected to only these 3 nodes. So I have to just update the values on these 3 nodes. Basically, I change the value here, then change the value here, and change the hash here, because value in its subtree has been changed. And then change the hash that is stored for the child here in this vertex, and all of these are now relevant. So I will keep a set of all the vertices that are relevant. I will check them one by one, and then if for any relevant vertex we can like find if for any relevant vertex we can find a child such that its hash is equal to the value at this vertex, then we will again perform that swap. So that's the whole idea of the solution, and it's like it's very cool because of this multiset hashing thing. So I will show you what I have done. So first of all, I took the inputs, and in like after taking the input, I'm also storing a random number for each thing. Random number for each element that is like each value that is relevant to us. Okay. So I made the edges of the graph, and then I'm doing DFS on those edges. Inside the DFS, what I'm trying to do is I'm storing the like this part is storing the hash of the entire, like hash of the values in the subtree. Like so hash of values, hash of IDs minus values in subtree. Okay, except and excluding value at vertex. Okay, because as we talked about earlier, we exclude one of the value, like we exclude the value at the root of the subtree. Okay, so we are adding the indices, we are adding the contribution of the subtree, because like it is definitely additive, and we are subtracting the value at the root of the subtree that are connected to this. Like basically this was not included in the children, so we are including it here. And yeah, so basically that's what we're doing, and we are also keeping the set of hashes of children. Okay, so I'm storing the set of hashes of children, and basically in this loop what I'm checking is if it is like ever equal to, like if the hash at this, if the hash of the value at this vertex is equal to the hash that I have stored at any of the subtree of any of the children subtree of this node, then basically I will perform this swap and so on. So yeah, so that's what I've done when I'm doing the swap. Like this is the part where I'm doing the swap. So I'm updating all the values, like the set of the parent of Z will change, and then the value of the subtree that we are storing here will be changed. The values will be swapped and so on. So this kind of work I'm doing, like I won't explain it line by line, but yeah, you can get the general idea. And this is a set named relevant, and this set stores all the vertices that might be having one of the red edges. So yeah, so these red edges are the ones that would be effective, that would be affected, and this set relevant is storing all of the vertices that might be having at least one red edge. So I'm taking the elements one by one out of this set, and then I'm trying to perform a swap, and if no swap has been done, then I just continue. But if a swap is done, then 3 vertices would be affected: the child, the main vertex, and the parent of that vertex. Just as I said, 3 vertices would be affected. So I just put it back into the relevant set, and yeah, so by the time I'm out of this loop, I have already done all the correct swaps and the permutation has been restored. So that's the point behind this solution. And yeah, so my code I have already submitted and it's accepted. So I guess the editorial solution would be probably different and not like mine. So that's why, I mean, that's the reason I made this video. And thank you for watching. If you want more contest solution videos, etc., subscribe to my channel, and I'll see you next time.